Now, we will discuss how to use Gauss' law to calculate the electric field. Okay. To do that, we start from the expression of the Gauss' law. Phi E is equal to the Q net over epsilon 0. And we also use the fact that the flux, okay, if we have the charge Q net inside a closed surface, we know that the flux that pass to the outer surface is equal to the integral of E dot dA E, we have that d phi is equal to E dot dA. We have discussed this before. So the total flux is equal to the integral over the closed surface of E dot dA. So you can see that we have E here, which the integral over the closed surface of E dot dA is equal to the Q net over epsilon 0. So it means that it is possible that we can calculate the electric field from this equation. However, to do that, our system needs to have symmetry. To simplify this integral and then to get the information of the electric field, if there is no symmetry, using this method to get the electric field can be extremely difficult. To see this clearly, it is better to see some example. Let us start with the simplest example, that is the electric field from the point charge. Okay, if we have a point charge Q, and if we want to calculate the electric field at this point, what is the electric field at this point? Okay, we can use the Coulomb's law to do this. But first, let us pretend that we don't know the Coulomb's law, but we know the Gauss law. And how can we calculate the electric field here? To do that, we will construct a closed surface. This surface may be not real. It is a we imagine that it's a closed surface that passes through the point that we want to calculate the electric field. We call this surface is a Gaussian surface. Which is not necessarily real, and in most cases we imagine this surface. Okay. Next, we have to look at the symmetry of our problem. In this problem, the charge is a point charge. So in this case, we can expect what is called the spherical symmetry. What is the spherical symmetry? The spherical symmetry means that if we look at this, if we construct the Gaussian surface here to be a spherical Gaussian surface, and if we look at each point on this surface, assume that this is a spherical surface, we should expect that we should have some symmetry on the electric field, right? Because if we are at this point and we look to this point chart, and if we move to this point and we look back to the point chart, we must see the same picture, that is just a point chart at the center of the spherical surface. So it's not reasonable to think that we should have the very different property of the electric field at this point and at this point. The electric field at this point and this point should be very similar from the symmetry. Okay? And one thing that we can expect that we can expect that the electric field should point outward in the should point in the radial direction. Okay. Radial direction. It is because if the electric field does not point in the radial direction, it means that if you look, for example, if we expect that the electric field point in this direction, it means that if you look at the electric field in this direction, and if you look at this direction, you will see the difference of the electric field. But how can that happen? Because if you look from this direction and you look at the point chart, and if you look this direction and you look at this point chart, you see the same thing, that is just a point chart here. So we should not expect that we will see the difference if we look at the electric field in the different direction. So the most reasonable choice is that the electric field should point outward, because if it points outward in the radial direction, when you look at the electric field from all directions, you will see the same thing. So we not expect this, but we expect this. Okay? Now, when we expect the electric field to point in the radial direction, you can see that E will parallel to the vector dA. Okay, we have that E is parallel to the vector dA. Okay, so it means that if we calculate E dot dA, it must equal to the magnitude of E times the magnitude of dA, like this. Okay, and the last consequence of the spherical symmetry, that is on a particular spherical Gaussian surface, we must have that E, the magnitude of the electric field, is constant. As I mentioned before, that when we look at E at this point or at this point, which are on the same spherical Gaussian surface, we should not expect that we see much difference. And since the distance from this point to Q and this point to Q are equal, so we should expect that E is constant. This is very useful because when we perform the surface integral E dot dA, which is from this result is equal to the surface integral of E dA. And if we expect that the magnitude of the electric field is a constant, we can put this E outside the integral. So we have that this equal to E times the integral dA. But what is the integral over the closed surface of dA? It is just the surface area. So we have EA, which the spherical surface area is a 4 pi r squared. So we have that this is equal to the 4 E times 4 pi r squared. Okay, which from the Gauss law is equal to the Q over epsilon 0. So finally we have that E is equal to the Q over 4 pi epsilon 0 r squared, which is the Coulomb's law. This is the Coulomb's law. Okay, so from this calculation we have the magnitude of the electric field, and the direction is point outward in the radial direction, which is agree perfectly with the Coulomb's law. So this is the first example, simple example that we can use the Gauss law to calculate the electric field.